Let's look at this data equation. Okay, so what all challenges are there in this inverse problem? So this data equation S is connecting the measurements to the desired parameter. We have seen that. Now S of course does not come by itself. What comes with it? Noise, right? So the S actual contains the ideal measurements and noise. So of course I cannot, I mean this is a real life problem, there is an antenna there, will be some noise on the receiver, so you will get noise corrupted measurements. But we expect this to be a challenge in any engineering problem. What else? So what happens is that I want to solve this problem, right. So argmin means that x which gives the minimum of this expression, S minus GS Ux, right. That's my solution, okay. So let's assume magically some oracle has come and given us this value of u, okay. Let's assume, okay, it's not realistic, but let's assume even if we had perfect knowledge of u, what is the problem? So this part we have already discussed, that the underdetermined system will have infinite solutions. So there is some more information that needs to be provided to, in some sense, reduce the infinity, right. So what I could do is, in linear algebra, if I am presented with an underdetermined system of equations, do I just declare that I can't do anything, or do I still try to do something? I use, we have all heard the word of a pseudo inverse, right. Pseudo inverses exist for matrices that are not square, right. What is the property of a pseudo inverse solution? For example, in an underdetermined system of equations, I can write a pseudo inverse and get some solution for x, and that x has what property in an underdetermined system? So those of you who remember your linear algebra, the pseudo inverse was the solution which had minimum distance from the origin, right, least norm solution. But which norm was that? Euclidean norm, right, 2 norm. So it had minimum 2 norm. So I can, if I use the pseudo inverse, I am basically saying give me the minimum 2 norm solution. They are one and the same statement. There may be some motivation to go for what is called a sparse solution, and I will give you a motivation why we would want a sparse solution. And that sparse solution comes by imposing a norm on the minimum 1 norm, instead of 2 norm, minimum 1 norm. Least energy is minimum 2 norm. And sparsity, so what does sparsity means? Most of the entries are 0, very few entries are non-zero. Okay, so we may wonder why should this be a solution? Why should I want to promote this? We'll talk about that. Okay, so if let's say, just assume for a second that I want a minimum 1 norm. In the next slides, I'll tell you why 1 norm is a good idea. But let's say I wanted minimum 1 norm. Then this optimization problem gets modified like this, that not only do I want to minimize the distance or the difference between prediction and measurement, right. This is my measurement and this is my prediction. Not only do I want this to be minimum, but I also want the 1 norm to be a minimum, and beta is some hyperparameter which I will determine numerically. So my ideal solution is what? One which minimizes both of them. Out of this infinity of solutions, I want that solution which minimizes this. And in the language of inverse problems, this, or even statistics, this adding more information is called regularization. That is the technical word for it. Okay, so I have regularized my solution by giving some more information. And what is that more information? Minimum 1 norm, minimum 2 norm, something else. It's up to me.
So how do you say this has any connection with?
Yeah. So why should this correspond to reality? Is the question, right? Why should my solution to this breast cancer imaging problem have minimum 1 norm? Okay. So now let's look at. So what we'll do is we'll just look at a property of 1 norm versus 2 norm, and then motivate why 1 norm is a good idea. Okay. So infinite solutions are there for underdetermined. Let's look at 2 separate cases. Okay. So this first case over here is where I have this blue line over here. So 2 variables, 1 equation. That's the simplest thing we can visualize. That 1 equation in 2 variables is what? A line. That's your blue line. So, I am calling it the data equation. Okay. And if I want minimum L2 norm, that is minimum energy, then what I can do is, so these red dashed lines over here, these are all circles of constant 2 norm, right. So, for example, this is 0.5, right, this one is 0.5 radius. So, I keep increasing this until I touch the data equation. So, when I touch this, what is happening at this point, the data equation is being satisfied because x1 x2 lie on the data line. That means I have got S is equal to GS ux, very good. And at the same time, of all possible solutions, can I say that this solution has the minimum energy? Yes, right, because it's just this is just a tangent over there. So, I say okay, very good, this is my minimum energy solution. But now when I look at the answer over here, it has some non-zero value of x1 and some non-zero value of x2. So, they are in some sense spread out. Okay. Now, when I look at minimum 1 norm solution, so this is my data equation as before. In this data equation, what am I doing? I am plotting now, these are constant 1 norm solution, constant 1 norm, because the locus for constant 1 norm is what? How do I define the L1 norm? Right, it is summation of mod xi. So, in the upper quadrant over here, what will the equation be? X1 plus x2 equal to constant, right. So, that is just line. So, these are all parallel lines that are expanding in the value of the 1 norm. Now, what is the earliest I can hit this blue line is at this point. So, this point over here, it satisfies the data equation because it is on the blue line, and it of all possible solutions, it is that which has the minimum 1 norm, right. Now, just look at the nature of this solution. Over here, you can see that this has a non-zero value of x2 and a value of x1 is 0, right. So, in this very toy example, it is a sparse solution because one entry is 0. If I expand this idea to multiple dimensions, this hyperplane will touch at some axis only, it will not touch somewhere in between. So, my solution will be sparse. So, this putting a minimum L1 norm tends to promote a solution which has sparsity. So, this is very clear, like when I in the previous slide when I said that imposing 1 norm gives me a sparse solution, you know why it does, right, and that is just geometry. Now, let us look at the critical question, why should my reality correspond to a sparse solution? Okay. So, here is where there is a little bit of signal processing that we need to look at. Okay. So, we are going to look at natural images, okay, and in signal processing or DSP you have looked at different kinds of bases. So, there are things called wavelet bases, discrete cosine bases, Fourier transform bases, various such bases are there, right. And I am going to look at a natural image, right, a cat is a natural object, so is also is a cross section of breast tissue. So, this is the original picture over here, top left, this is original, which has some how many 46,000 pixels. So, in order to represent this picture correctly in the pixel domain, I need 46,000 numbers, right. If I keep I use what is called a Daubachy's 4 wavelet basis, you need not know what it is, but it is some kind of a orthogonal basis. In this orthogonal basis, if I keep only 1/4 of the coefficients, only 1/4, I get this. Can you visually tell any difference between these two? Right, visually it is almost, I mean it is next to impossible with the naked eye to tell any difference between these two images. But what have I done? From 46,000 plus, I have kept only 1/4 of the coefficients. So, only 10,000 coefficients were needed. Then I got a little bit greedy, I did a little bit more optimization within this wavelet domain, and I keep only 7% coefficients. Now, I can see that it is a little fuzzy, but I can clearly make out it is a cat. I can tell you where the eyes are, where the nose is, where the ears are and so on. But how many coefficients have I kept? Right, roughly 3,000 coefficients. So, when I started from 40,000, I am down to 3,000 coefficients. Then I got even greedier, I said okay, let me keep only 2% coefficients, right. When I keep only 2% coefficients, this is very fuzzy, But if I wanted to, if my information that, if my question was where are the eyes, I can still answer the question. If my question is how many whiskers are there, I cannot answer this question, right? So this is sort of a very good motivation why, if my imaging domain, instead of looking at it in the pixel domain, which needs 46,000 numbers, if I transform it, a linear transformation, it's a linear transformation, the wavelet transform is a linear transformation, means it can be characterized by a matrix, simple. If I choose the correct matrix, I can, with just 2% coefficient, so 2% of this is going to be roughly how much? Less than 1,000, right? 800 or whatever, yeah, 900 or something like that. With 900 numbers, I can get a solution that is so good, right? And when I keep 2% coefficients, what have I done to the remaining 98%? I've set them to 0. So in the wavelet domain, this image is sparse, very, very sparse. Only 2%, 2 out of 100 numbers are non-zero, rest are all 0, right? So but I mean, this is the place where I am using a priori information. I am using the a priori information that the cross section of breast tissue is a natural image. I know, I mean, empirically it has been observed that natural images are sparse in wavelet domain, in discrete cosine domain and so on. So this is me using a priori information and solving the problem in the wavelet domain. Why? Because the number of variables there are lesser. Yeah, the other great thing is that we don't need to know which coefficients are 0. I can, when I solve the minimum one norm solution, I don't have to tell the solver these coefficients are going to be non-zero. It can figure out which numbers are non-zero. Yeah, so that's actually what we have done. So for example, this is the original image. This is what is called a level 1 wavelet decomposition. This is a level 2 wavelet decomposition. That's what has happened. I mean, these are not separate wavelet transforms. These are wavelet transforms to different levels, right? So this is level 1, level 2 and level 3, right? So they are all related. They are not unrelated. Okay, so if you study the theory of wavelet transforms, you will know how they are very related. You can go even more. You don't have to stop at 3. Right? So the field where these problems are studied is the field of compressive sensing. So compressive sensing means I am trying to get sparse solutions from undersampled data. I have undersampled data and I want something that can recover the solution. Okay. All right. So now let's look at a few more issues. So okay, why? So minimum L1 means what? We have seen that minimum, when you go back over here, minimum L1 meant sparse. I know beforehand that my object is going to be sparse in the wavelet domain, right? So that's why I am going to solve my problem and enforce minimum L1 norm, so that I know I'll get a meaningful solution, right? That's the logic. So this was one problem. I mean, what we were discussing so far was the problem of not having enough information, right? Not having enough information is what is a technical word for it is ill-posed. So the inverse problem is ill-posed. There is not enough information there. I have to give additional a priori information. It is sparse, it is this, band limited, it is this and that and all of that. Okay, that is a priori information. The second problem that we are going to talk about is the problem of non-linearity. So what we assumed so far was that the field U is what? We had said magically someone has given it to me and we were only worrying about 1 norm or 2 norm. Now let's come back to real life where U is also not known, right? So in this problem, this Rx is the regularization. This can be 2 norm, it can be 1 norm, it can be wavelet something, whatever, right? Let's just leave it out, leave the details out. But the main thing is that U is not known. We have not yet come to that problem. So let's see what happens here. So you may say that okay, U is not known, no problem. I have a state equation. That state equation told me that there is a relation between that, use the matrix GD. So if you give me E and if you give me X, I can estimate U, and that U I can take and put in over here. That's what I can do, right? So what can be a strategy to solve this problem? Start with some guess for X, okay, put it into this equation, get u from there, put that u into this equation, and then I am done. I can solve this. This becomes a problem only in one variable x, right? Sounds reasonable? I could do that, right? And if I do that, there is a name for it, discovered late 80s, early 90s, called the Born iterative method. So it's an iterative method, starts with some guess for x, calculates u from that, and puts that u into the data equation and gives me the x. Okay?
Just one thing.
Yeah.
What is the small x?
This x.
No, the argument, yeah.
Are what is my variable of minimization is x, that is written below the argument. X is contrast, permittivity minus 1. That permittivity minus 1 appeared everywhere, so I called it one variable x instead of having to write something minus 1, so x. So this was the Born iterative method. Now strictly speaking, when I go to minimize this problem, those of you who have done a little bit of optimization, you should know how will I minimize this. Forget optimization. Supposing I give you a function in one variable and I ask you find the minima of it, what will you do? You will differentiate it. In fancier language in optimization, what would you do? You will find the gradient. Basically, ideas of differentiation. Now this object over here, u over here, what are we doing? We are substituting some value based on an initial estimate of x. That's what we are doing. But when I go to take the derivative, are we keeping u to be constant, or if it's a number, then it's a constant. I cannot take the derivative with respect to x for u also. But actually it is. U is a function of x and that function is here. So if you are very, very strict, what you should do is you should take this u and substitute it into your original equation to get this one. This is your u, right? Gs u x, Gs u x. Now I have eliminated any intermediate variables. It's only an equation in x, right? Because s is measurement, Gs is known, Gd is known. I have my x over here, I have my x over here. So this is a very complicated looking equation, but it's an equation in one variable, one unknown, not one variable, one unknown x. Why did we do this, right? Oh, why did I write this as a diagonal? Okay, I was hoping to not get into it, but let's write this over here. So this u into x over here that appears everywhere. If you notice in the integral equation, what was the actual thing? It was chi r prime e of r prime, right? And then the g over here, and this whole thing was integrated dr prime, right? So this thing over here, they always appeared in the language of linear algebra. It was like writing xi ui, right? So it was a column vector with xi ui. Now how do I write this xi ui in terms of x and u? I can write this as an x like this, x1 xn multiplied by u1 un, right? It gives me the same thing. This is 0 and this is 0. Or I can also write this as u1 up to un and a column vector x1 up to xn. Yeah, that's why you notice that there sometimes it is small x, sometimes it's capital X, right? So when I write it as capital X, I mean it as the diagonal version. That means, so this is capital X into u and this is capital U into x. Okay. But since we are not solving this right now, I am just leaving it like that, right? So that's why this whole thing becomes diagonal of whatever I get. Whatever I get is going to be a column vector. I need to put into a diagonal matrix form, right? How do we choose the initial value of x? What is the most? What would you do if you were trying to solve it? 1. Why 1? Well, you can do 1. This is x, not permittivity. This is contrast. 0 contrast. So 0 contrast is actually the most popular starting guess, and there's a name. It's so popular. There's a name for it which is common in not just in inverse imaging but also in particle physics. called the Born approximation. Right. To begin with. So, this integral equation that we got comes in quantum mechanics scattering equations also. So, say this is the same Born from quantum mechanics, okay. And the physics people call it Lippmann-Schwinger equation, and electrical engineers call it Friedholm integral equation, okay. It's the same thing. Now, what is the problem with this equation? It's exact. So, when I go to take the gradient of this, it has everything inside it. There is a x where it should be, unlike this equation where u appears to be just some number, some constant, right. So, this is misleading. So, if I wanted to correctly find out the gradient, I should use this equation, and finding its gradient is a lot of hard work, okay.
Why x equal to 0 then?
Initial guess, you can choose anything you want. I am just telling you what is common.
The x equal to epsilon r minus 1, right?
Yeah. So, if you choose x equal to 0, means you are assuming vacuum everywhere and you are building up from there. You need not. Will the iterations lead to the same guess or not? It's a very good question. In this Born iterative method, the question is, will I arrive at the same point regardless of what guess I take? Yeah. Will I get this finally the same x? Answer is I don't think so. Answer is don't think so, and that's correct. Don't think so. Why? Give me a precise reason why. You have enough information on the slide to tell me why. Multiple, right? So, if my cost function, let's say I have a variable in one this thing, and if my cost function was a nice parabola, regardless of where I start, I always end up at the same point. But if my cost function were multiple minima, right, then of course it matters where I start from. And look at this cost function over here, this objective function. It's anything but a nice parabola, right? So, where you start from matters, right? Actually that is one of the major issues in this problem. So, let's actually look at it a little bit more quantitatively. Okay, so we have already said that ill-posed, not enough data, and non-linear, right? This equation over here is non-linear in x, that's the problem. So, let's see the manifestation of this non-linearity in how does it affect us. We know it's going to affect us, but how is it going to affect us?